就开始，不过因为美国的飓风3D 的导弹，所以严教授呢就晚一点到这边。我想，各位同学会来的都是有一点东西知道。严先生会讲一些有趣的东西啊，这是美国的一个可以讲说一个有名的学校，对不对？就是Cornell University 啊，可以听到这些东西啊。前后我们大概6个 lecture 啊，所以除了这一次介绍以外，严先生就自己会上台，就不需要再做介绍啊。那么这个lecture 的名字叫做CLO 这个 lecture series 克洛我们的很老的教授已经过世很多年了。的纪念演讲，纪念 lecture， 那我们欢迎，热烈欢迎这个，大家拍手。
Thank you for the introduction. I'm very honored to give this series. Oh, I should turn on
Does that help?
Yeah.
Can you hear me now?
Yeah.
Good. Professor Crow was a unique person when I was a student at Taida in 1950s. And I still remember every time he walked to the podium, he would give us a salute and then a bow, and then we'll start talking. And then he will write something on the blackboard, and then if you heard something in the back, he would take a piece of a chalk and then will hit the person right on. But anyway, I feel that I learned most physics in Taiwan from him. So I'm very honored to give this series of memorial lectures in memory of Professor Crow. Now, as Professor Huang just mentioned, that originally it was scheduled to give 8 lectures, and now it's reduced to 6. And when I went over the material I want to cover, I still feel that I can do it in 6 lectures. But in doing so, I will skip most of the details because I assume most of you have taken a course on a standard model somewhere. And so I don't have to go through the details. And the title of my series of talks for the story behind the standard model. It means that I try to, the data cannot make a proposal that the data should have some kind of scaling properties. Essentially, a function of 2 variables. He proposed that in some limit, it only depends on the ratio of the 2. Now, this scaling, Buchanan scaling, became the beginning of the whole era of the new particle physics. But do you know why he made such a proposal? What's the motivation? Somehow, when we read the textbook now, the people don't mention why he made such a proposal. And in this seminar, I would like to give you ideas of why he made a proposal. So what I'd like to to, as I said, is to give you, so instead of giving you a polished, finished product of a standard model, I will try to recreate the process in which the standard model was born, and it grew up to become a theory which described the strong interaction and the weak, electro-weak interactions. So the purpose of these lectures, I hope, is to give you some sense how the real research is done in the real world. Now, I've never given lecture in this way, so whether they will be successful or not, I don't know. We just have to wait and see. Okay? So, let me give you the list of the talks I would like to give. So this will be lectures. Are the characters too small? You can see in the back. Okay, okay, I'll try to write bigger. So the one will be so this lecture, the first one, I'll talk about the physics in 1968, and there are 2 points. One is why did I pick 1968? I'll tell you why. Secondly, the reason I will do this is because this will provide a baseline, so we know where we start. So that will give you a review of the particle physicists know at the time. Then the second lecture, I'll talk about in the second lecture, I'd like to tell you the Adler's neutrino sum rules, which follow from current algebra, and then tell you why Biot proposed his scaling, and then how Feynman proposed the pattern model. Okay? Then the third lecture, I'll talk about operator product expansion. And then asymptotic freedom. And then QCD. And I will show you that the QCD is unique in the sense that all the experimental evidence requirements will lead us to this QCD as we know it, okay? Then the fourth lecture, I will talk about the wind-up Gratian Salam, and then the spontaneous symmetry breaking, Higgs mechanisms, and then dwarf. So Tuve made a major contribution that by showing that this model is renormalizable, and it's a very important point. And I'd like to tell you a little bit of the stories. And then 5, I'll talk about neutrino masses. differentiation. And this will have some Dirac mass, have Majorana mass, and then also mixed of both of this and that, okay? And the sixth, I still don't know what to talk about. And it's possible that some of the topics will take more time to do it. In that case, we just have to push the lectures downward, okay? And this topic actually was encouraged by Pouch. I originally did not think I would do this, but he said I should do it. So actually I started learning, and I learned quite a bit of. So I'm very grateful that I learned something because of your encouragement. Okay. So let's talk about why 1968. Two events happened in 1968. One is a big event, and that's the MIT SLAC deep elastic electron scaling. And then, as I said, that this experiment opened up a new era for particle physics. The second one is a small event. It's personal. I happened to get my PhD in the same year. From Harvard. And at the time, got two offers. One from Institute of Advanced Study from Princeton, the other is from SLAC. So when I received the two offers, I thought about it, where I should go. You probably couldn't imagine, but when I was an undergraduate at Taipei, Einstein was at the Princeton, and Yang Zhenling, Professor Yang, was also there. And so everybody look at the Institute for Advanced Study as somewhere, it's the peak of a mountain that you want to climb to. So when I got this offer, I thought maybe I should go there. On the other hand, I was at Harvard for 5 years, and I only talked to theorists, had contact with the theory, no experiment. And then I thought that physics is experimental science. So I should go somewhere there is a real experiment going on. So I decided to take the offer from SLAC. So this decision was purely logical, nothing. I did not consult anybody. And then a few days later, my advisor Shrink asked me, have you decided where to go? I said, yes, I wanted to go to SLAC. Oh yeah, so you said you made the right decision. I said, why? Because they are doing an extremely important experiment. I said, almost fainted, because why didn't you tell me what happened if I made the wrong decision? So you know that sometimes the fate and the luck, it just, you could not resist. So there's no way that somehow I was lucky. So, and this year, 68, is this experiment. This, of course, lead to a formula become QCD. But you may ask, what about the electron weak? Yes, you know that the Grashow, I don't remember, published the paper in 1960, 62 or something, I don't remember. Anyway, I know that Weinberg published his paper, which later he got the Nobel Prize for, was 1967. Okay. So the interesting thing is that when this paper, oh, by the way, I confess I never read Salam's paper because I don't know. It was not in the journal and I didn't. So I only give you these two ideas. Now, what I was going to say. Oh yeah, when this paper was published, nobody paid attention to. For example, in the Weinberg's paper, between 1967 and 1971. Why 1971? 71 is the year when the two discovered the how to renormalize the theory. So between 1967 and 1971, only 3 citations of this paper. Even Weinberg himself did not work very hard on it. In fact, he gave the problem to his student, asked his student to see if he can find a way to renormalize the theory. And of course, his student failed. It took another student to work. Wolf is a student, is a graduate student, and he succeeded. So, even though, but 1968 and 1967 it's roughly the same time, so 1968 is good enough. Okay? Oh, by the way, yeah.
You mentioned nobody was paying attention to Weinberg's paper, but Tooth did take it seriously. And how about the other people? Do they also consider doing renormalization to that theory is important?
You mean other people?
Other than Tooth? Is it widely? Yeah.
Oh, lots of people try to renormalize, but nobody succeeded.
So it was recognized as an important problem, just nobody made
it's just impossible to solve at the time.
So that's the reason it has so few citations, because nobody can solve it. So the citation becomes small.
Right. And then after 1971, the number of citations just turned to the roof. Okay. And then if you read the Weinberg's paper itself, you'll find that near the end, he said, the theory may be renormalizing. Okay, he wasn't sure, and then but he said, after spontaneous symmetry breaking, things seems to look different, and so he didn't want to make any other bet. Okay. By the way, please interrupt, ask any questions, even in Chinese. That's fine. I don't see many. Our foreign guests, so you can speak or you. Anyway, try to feel free to interrupt, okay? So, what are the particle physics in 1968. Well, the first thing to tell you is QED, because that's the most successful theory the physicists ever had. So, QED. Essentially, QED is QED. It's finished. It's very good, and it worked very well. And there was no discrepancy discovered anything, but and also the fine structural constant is so small, it allows perturbation expansion, so you can really do calculations, and let me just give you some examples. One is the lamp shift. And that's the energy level between 2s, J1 half, and minus 2p, and J equal to 1. And if you use the Dirac equation, you'll find that these two levels, as long as the J is the same, the two levels are degenerate, but Lamb discovered that that's not true, and roughly about 1050 kilohertz. The Lamb was able to do this experiment because of the World War II microwave technology, and so in some way the war effort made some good for science. Now this, of course, right now this measurement is much better than this one, but there's a limitation to how well this shift can be measured, and the reason is that the hydrogen atom involved the proton here. And then eventually you have to know the structure of the proton very well in order to compute this energy difference. And we are limited by the information about the structure of the proton. So this is not the best quantity to measure. The best quantity you can measure is this, called anomaly. Making moment. Of the electron. And we all know from undergraduate ENA, the potential energy in the magnetic field due to a magnetic moment is given by this. And this mu, the magnetic moment, is the G factor, E over 2m, and then times S. This S is the spin. So let me give you this number. G is G here, equal to 2. And that's from the Dirac equation in 1928, I think. Right. Then the next one, alpha over pi. And that's Schwinger's contribution to QED in 1948. Now these two numbers, this one gives Dirac a Nobel Prize, this gives Schwinger a Nobel Prize, but then the next number doesn't give anybody a Nobel Prize. The one is alpha over pi squared, and then there's a factor 2 here, I'll write it down here, 197, 144. And then plus 1/2 minus 3 log 2. And then plus 3/4 zeta function of 3. This was computed by Charlie Summerfield. In 1957. And Summerfield was a Schwinger student. Before he did the calculations, some other people got the results. And Schwinger was suspicious. The result didn't look right. So he assigned this problem to this one, and he got it right. Now, when he got the answer, Schwinger, the story, I don't know if it's true or not, but the story is that he made an estimate. How long will it take to do the next order calculation? the sixth order calculation. And then after some estimate, the conclusion was a lifetime. It took a lifetime to finish. So Schlegel just came out. Now, it turns out that his prediction, his estimate was pretty good. The sixth order calculation, I have the answer, but it's too long. I don't want to compute it here. It's no. Analytical. But this is in 1996. So it took 40 years. And not just by two people, one people, but different groups working on different diagrams. And then after 40 years, they came up with an analytic answer to it. Of course, before this one, Kinoshita. He is a colleague of mine at Cornell, and he is the #1 calculator in this business. And he did this kind of calculation long before 1996, but by computer. And he also went on to do the 8th order. And then before I left, he told me a paper. He just finished with some Japanese collaborators on 10th order. So he just, now he is 88, but he's still going very strong. It's a very incredible person. And as far as I know, there's no discrepancy between theory and experiment. Now, actually, after this order of S order, the accuracy of the alpha, the structure constant, and everything. Wow, the bubble is smarter than the ones I have at Cornell. I have to push up and pull the other down, but this one, some will do it simultaneously. Huh? It's very beautiful. Okay, anyway, the structure constant, a fine structure constant. Experimentally, the accuracy is not enough to put it in here to compute the G for it. Because the accuracy is not experimental accuracy. To predict G to this order and higher. So what Kinoshita did was to use this expression and going backward, because the G, the anomalous moment of the electron, has been measured very precisely. So use that experimental value to compute what alpha is. And it turned out the alpha determined by this way is the most precise value for alpha known so far. Okay? So that's the story about the QED, and then the other one is the third one, called radiative correction to a Coulomb scale. The reason I mentioned all these three successes is to tell you that in order for a theory to be accepted by a physics community, you don't have to predict everything. all you have to do is to predict 2 or 3 things. And those are the 3 things that the QED predicted after showing the Feynman and Tomonaga to work on high order corrections. And everybody accepted. Okay? So there's a turning point that in the beginning, the theory have to convince the experimentalists that this is the right thing to do. And once the experiment confirm the theory to some extent, then the thing is reversed, that now theory will be accepted to be true. And then you can just do more predictions, and the experimentalists will try to confirm them. Okay? Okay. So that's the QED. And the next one is talking about the no, the earliest the beta decay is the earliest one. And that was the process that people discovered, the decay of a neutron. And they found that the energy of the electron and then number of electrons here. And then they show something like this. Anyway, if this is a 2-body decay, then you know in the center mass of the neutron, then the energy should be a delta function, right? Because the momentum has to go opposite. So momentum is fixed, then the energy is fixed. But it turns out that it's continuous. So the energy is continuous. And then this maximum is equal to E n minus E p. So it appears that the energy is not conserved. And then this, I'm sure you heard the story, that the Niels Bohr then proposed that maybe the energy conservation is no good for the beta, for weakened junction. The reason I mentioned this story is to show you a great physicist like Niels Bohr can do crazy things when things become desperate. So because this is really desperate, because our energy conservation doesn't work and so on and so forth. But of course you know that the energy conservation is good. But the Niels Bohr just did not find the right solution. The right solution was according to Pauli in the 1930s. He proposed that there should be another particle called neutrino. Actually, originally called neutron. But the real neutron was discovered in 1932. So this cannot be called neutron. So what happened? Fermi constructed a theory, and he calls it neutrino. Neutrino means a little neutron. So this is neutrino. Okay? Now neutrino has the property that the one is that the electrical neutral then has a spin 1/2. The reason it has to have spin 1/2 is that otherwise the spin on both sides don't match. This is the spin 1/2, and this is the spin 1/2, this is the spin 1/2. If without this, then the disk can only give you integer spins, but this is spin 1/2, so this has to be spin 1/2. And then because of this, that the neutrinos are massless to the accuracy of experiment. So So 1930s, Pauli proposed the neutrino. 1934, then the Fermi proposed this interaction of Lagrange. For something like a G CO2, and then P, some gamma, I, neutron, and then electron, and then some matrices and neutrinos. Okay, something. Now Fermi use gamma I equal to gamma mu. And then, but of course, in general, this gamma I can be 1, gamma 5, gamma mu, gamma 5, could have sigma mu nu, could have sigma mu nu, gamma 5. So there are lots of possibilities. I listed here because later I'll make a point about this. Okay? So that was 1934. Then in the next 30 years, what happened? One, of course, is the parity violation was discovered. And this, of course, Li and Yang proposed in 56, and C.S. Wu and others confirmed experimentally in 1957. Okay. Okay. Then the other one is the V minus A fluid. That means this gamma I is equal to gamma mu 1 minus gamma 5. Okay? Then number 3 is that the two neutrino. They discovered that the neutrino associated with the electron is not the same as the neutrino associated with the muon. And this was discovered in 1962. And by Lederman, Schwartz, and the Standard. And then for this, they received the Nobel Prize many years later, okay? And the way they did is this. You take a pion, decay to a mu plus or minus plus a neutrino. Now there's also a possible decay like this. But it turns out that even though the free space is much larger, it turns out the branching ratio is much smaller. And I'm sure you know why, so I'm not going to discuss that. Now they take this neutrino and then interact with the protons. So this neutrino here going to mu plus mu minus. Or mu bar, okay? Because they also put the mu bar here. And then mu bar P and N plus mu plus. Okay? But then, this they found. okay? But not the form. The nu plus n going to p plus e minus, or nu plus p going to n plus e plus these two north. That means that this neutrino associated muon can only produce muons. They cannot produce electrons. So the conclusion is that these two neutrinos are different. Nowadays we know that each lepton has its own neutrinos. So here we found two. Then the next one is the CP violation. This was discovered in 1964, and this was also found from K-long decay to 2 pi. Okay? And the Professor Shum that discussed this 2 days ago, right? So the symmetry, symmetry somehow is broken one by one over the years. The other one is called conserved vertical and it's called CVC. And the idea is the following. You have 2 decays. One is the beta decay. And then there's muon decay. Mu decay to E minus plus nu E plus nu me, like that. Okay? So if I write down the Lagrangian for the beta decay, it will be written this way. P bar gamma mu 1 minus GA. You don't worry about GA. Just N, and then E bar gamma mu 1 minus gamma 5 continue. And then decay for the muon is called C mu over square root of 2. And then you have mu gamma mu 1 minus gamma 5 muon, and then I have an electron, and then a gamma mu 1 minus gamma 5 neutrino. Okay? Now it turns out that the experimental you can measure just decay rates, and it turns out that the G equal to G mu experimental. And then the question is why? Well, you may ask why is why. Well, the reason is this. You may assume that the 2 coupling constants are equal as a bare coupling constant, but the proton and the neutrons have very strong interactions, so they must have strong interaction correction to it. But the electron and the muon don't have any strong interaction. So how come that even if you assume the 2 coupling constants are equal when they are bare coupling, how come the renormalized coupling constant is still the same? Okay? And that's the question. Now this should remind you of the following. why the electrons are charged and the electric charge of the electron and the electric charge of proton also the same, experimental. And then you can ask the same question, because the electron doesn't have any strong interactions, but the proton has lots of strong interactions. So we know that even you assume that the E of the pair coupling constant is the same as the pair coupling constant for the proton. How come? The after renormalization, that they still are the same, okay? And this we understood. It's because the electric current, electromagnetic current is conserved. So it's a consequence of current conservation. And therefore, maybe one can find a similar explanation there. And indeed it is. And the reason is the conserved current is the isospin current, okay? Because we know that if you take the nucleon as a proton and a neutron as an isotyplet, then the isospin current and this tau is the Pauli matrices. Then this current is equal to 0 because of the isospin conservation, isospin symmetry. And so, because of this, at the G for the beta decay and the G mu for the muon decay stay the same after renormalization, okay? Now, this is extremely important observation, and the reason is this, I want to mention here. This is the isospin current. It's a strong interaction symmetry. Isospin symmetry, right? But this V minus A is V current. Is a weak induction. But somehow, this current and that current are the same. And so, the fact that these two currents are the same, give you a connection between the strong induction. And in particular, that give you this identity, this equality of the two coupling constants. And to tell you the truth, I don't understand why this symmetry current in the strong induction happen to be the weaker. If any of you know the answer, please let me know. I really appreciate it because for many years I couldn't figure out why this is the case. Okay. This only talk about the isospin current, but later you have a V minus A, and the same thing here, a V minus A, and there's still, it's a mystery to me why it's the same. The reason I say that is because if you look at the gamma I there, it happened that the weaker interaction pick out these two possibilities. Suppose that the weaker interaction there is this or that, and then the connection will not be there, and so then the strong interaction symmetry and the weak currents will have no connection, and then we'll lose the equality of this, for example. So I don't understand. Can we take a 5 minutes break? So I'll come back after 5 minutes. I should have finished the whole story before we had the break. But anyway, I said that the two coupling constants are identical, but turned out it's not quite true that the G is only about. There's a little bit of discrepancy here, and we now know that this is due to Capippo angle. And the Capippo angle, of course, is part of the CKA matrices. Now, I want to make another point here, and it's my own observation. It's good to start with this first. Then you get the CVC. And then once you get the CVC, then you can go on to talk about Capippo angle. So you get both. You start with the fact that the G not equal to G mu, then many people will say, well, that's obvious, right? And so you will not get this, you will not get that. So in physics, it's very interesting that it's a sequence of observation or sequence of discovery is very, very crucial to how we understood these things. Let me give you another example. When the MIT SNAG experiment discovers Biochemical scaling, actually at the same time, some experimenters discovered the data is not quite scaling invariant. There are some scaling violations. But in my impression, the SNAG authority suppressed that data. The reason is that they want to promote the scaling. So they got the scaling right, and then later scaling violation came out, and they also said, yeah, of course, we found a scaling violation. So they got both right. Now, if the scaling violation was announced first, then there will be no Biochemical scaling, and then nobody will talk about, it would be totally different. So it's this kind of things play a big role in the evolution of the physics, and you have to be aware of that. Okay, so the next thing we'll talk about strong interaction. So this is strong interaction 1968, more or less. The first thing to say is that there's no theory for throwing options. In particular, there's no field theory for it. People will talk about pseudo-scalar coupling. Ion coupling, something like that. Or you could have gluon coupling, neutral gluons. So what do I do? And several models. But the problem is that these are called model field theories. And the problem is that there is no theoretical justification or any motivation for proposing these theories. That's one thing. The other one is the coupling constant is too big. For example, this here, G pi n square over 4 pi. It's something like a 15. And so you cannot use the perturbations. So the field theory in the 1960s for strong interaction, nobody believed anything in field theory. So at that time, there was an approach called S matrix, called bootstrap. And of course, this led to a very complicated mathematical schemes, but again, there's no progress. In the meantime, many particles, new particles have been discovered. So, new particle. So the question is, what do you do with these new particles? It's clear. Well, it's unlikely that every particle is an elementary particle. So this gives you a attempt to find a organizing principle. To understand the pattern, okay? And there are two things. One is that Kelman and Niemann. Yeah. in 1961, proposed a group called SU3 to organize these particles, and you know the low dimension representations 3 and say 8 and the 10, okay? Now all the baryons and the mesons can be organized into 8 octet or decoupler. And I'm sure you saw the pictures before, right? Something like this. I don't think I have to tell you what these particles are. Just give you an idea that they all can be organized in this form or decoupled. Let me write this down here. Anyway, something like this. Again, you ask the question, why Gelman and Niemann propose SU3? Because around that time, many other kind of groups have been proposed, O4, W4, W3, and many others, okay? And this is another observation of mine. When a great physicist in his peak of a creativity, everything he said, everything he did is correct. And for some reason, that's true. I mean, in the 19, something like about 10 years period, everything that Gelman said became a part of physics. And they just, it's some of the intuition and the creativity just never failed him. I don't know why. Other very good physicists came up with other groups. Those are wrong groups. The group he came up with is correct group. Anyway.
Does he do any calculation or just basically see it?
Calculation on?
Well, when you say he basically come up with all this result, does he actually do the calculation first or he basically?
No, he just look at the patterns.
Right.
Well, some calculation, a little bit. The mass formulas, how to compute the mass differences between the different spin, isospin, or something. And for example, this particle, omega minus. This was the mass was computed using some mass formula, and it's predicted. And so when this particle was discovered in 1964, it was treated as a triumph of SU3. Now the idea, the reason why this simplest representation, 3, this is missing. It's an intriguing fact. But then Gelman and Choi independent by in the same year, I think. Yeah, 1960. Proposed that these are called quarks. Okay, in representation 3. And then these quarks have very peculiar properties, as you all know. And then all the baryons can be written as the bound state of 3 quarks, and the mesons will be Q bar Q of bound states. Okay? But the quarks have a very strange properties because they have a fractional charge. Electric charge. So all the observed particles have integer charges. So for example, other interesting properties such as omega actually is a minus. It's 3 strange quarks. And so these are 3 identical particles, and this is in a ground state. So the spatial wave function have no relative angular momentum because they are the ground state. Are symmetric. With respect to interchange of the 2 quarks, and then the spin wave function is also symmetric because the total spin is 3 half. You know, if you have 3 spins, the highest spin is always symmetric. So spin 3 half is symmetric. So somehow these fermions are quarks, but they have spin 1 half. So these quarks seems to violate spin statistic. Connection. And then quite a few people proposed a solution to this. And the solution is that there's several people, Greenberg. In 1964, Han and Bu, (1965), and then Nambu himself, 1966. Anyway, the solution is that to give the quarks an additional quantum number. And this we all know is called color. Okay? And then if you have a color, then you can write the omega minus will be equal to, you can say epsilon alpha beta gamma, and then you have S alpha, S beta, S gamma. Then you see that now if you interchange any 2 of them, it's antisymmetric. So this restores the spin statistics connection. And furthermore, they propose that only color symmetry can exist. And then of course, this is known as a color confinement, quark confinement, and those things. Okay? So for example, you might ask why you don't have QQ bound states or QQQ, because they cannot form color singlet, so those states would not exist. Now this color confinement is a nice idea, but this is one thing in the strong interaction which has never been proved. It's taken as a working hypothesis, but nobody, as far as I know, that has proved this point.
So why Gilman himself? Why Gilman himself did not propose this?
Who?
Gilman.
Gilman?
They proposed the
Color?
new color, yes.
He did it only after this people.
Yeah.
You know why he did?
Why he didn't?
I don't know. I guess even if
He
you
knew the problem, right?
I know. Yeah. Even if you are greatest physicist, you still have to leave something for other people to do. Otherwise, yeah, I know. It's Gilman didn't do it. It's interesting. Okay, let me discuss one more thing. About current algebra. Now, if you take the, I erase it, but oh yeah, here. If you take a model field theory, say using the quarks, not the nucleons, then you can have Q bar gamma mu, I d mu minus G d mu Q, and then I know it's plus or minus, I forgot. Then we know that the quark mass is very small. This is called a current quark mass. So if we drop the mass term here, then this model field theory has two symmetries. One is maybe yeah. One is the quark going to this is the vector symmetry, and then the other one is a chiral. Gamma 5. then you can show that this Lagrangian is invariant under these two transformations. And then the corresponding current, which will be conserved, are vector currents and actual vector currents. So and then actual vector current. Okay. And this current, oh, I should say one thing. If you have both symmetry of this kind, then you expect that for a baryon with even parity, there should be another one. With R parity. And the same mass. But we don't see that. We don't have a proton with an even parity and a proton with the R parity. So this symmetry must be broken. So the idea is that this chiral symmetry is broken. Spontaneous. Okay? And you have this kind of symmetry breaking, then there will be goldstone bosons. And the pion are the example, then there will be other pseudoscales, etas, and those things. Okay?
So this is
Now, coming to this.
the chiral symmetry breaking is from
Right?
Bambu.
Say it again.
Who gave the chiral symmetry breaking and goldstone boson? Who gave that idea? First.
I don't know. I don't remember. Nambu is one of them. I don't know who else.
So it's Bambu and also boson?
Maybe goldstone also.
Okay.
Yeah. Some of the things took for granted and forgot where they came from. Yeah.
In the other sense, why do they choose the chiral symmetry?
Huh?
If you have two symmetry here, why do
Yeah.
you choose chiral and not vector?
Well, actually, it's V minus A, V plus A,
Yeah.
the two.
Mm-hmm.
This one is okay, but this one is broken.
No.
No.
So because of V minus A?
Huh?
Because of V minus A?
No, no,
Every
that's,
time you do so V minus A also V plus A.
I don't know, we say chiral is 1 minus gamma 5 and 1 plus gamma 5.
Yeah.
Anyway, those currents I wrote above, they satisfy some commutation relation. Well, first of all, these generators, as you see, satisfy this commutation relation. And then the current V0A X T satisfy the commutation relations A, B, C, V, 0, C, X, E, 3. And then I will now write them all down. V0, A, 0, B, same thing, here the same. Here's the A, 0, C, and then you have A, 0, A here, A, 0, B here. Then this will be equal to I, F, A, B, C, A becomes V. Okay? And this is called current algebra. What's interesting is that they just follow from canonical commutation relation of the fermion field. And even if the currents are not conserved, you can show that these commutation relations still hold. So this current algebra is more general than the theory implies. And this gives rise to two things. One is a lot of soft ion physics. Oh, I should mention one more thing. This actual current is equal to f pi, m pi squared, and then a pion field. I, okay. So this is called PCAC. Somehow the divergence of actual vector current is proportional to the pion field, and it's called partially conserved actual current. It's partially conserved because this is not identical to 0, or proportional to this. Okay. Now, this current algebra plus PCAC give rise to lots of soft ion physics. And Steve Weinberg and others did lots of work on this subject. Now, one of the motivations for proposing this current algebra by Gell-Mann was to do the following thing. You have protons, neutrons, and then you have sigmas, your lambdas, all kinds of particles, okay? Lots of particles. Now you want to write down some current, a weak current. Say V. Now you have a term for P we wrote down before. And but then all the other particles, what do you do? Also pions, Ks, and so on. So you have to write down each term. That's all. Now, it's not so obvious that how do you normalize it. Each term may have a coefficient square root of 2 somewhere somewhat. So how do you determine which coefficient to use? Well, the current algebra gives you a way to do that because the current algebra is nonlinear. You see the VV equal to A equal to V, and VV equal to V. So the scales are fixed by this current algebra. So one of the motivations for Gell-Mann to propose this current algebra is to normalize the contribution from different particles to the weak currents. Okay? Now, this is another thing that when you write a paper, there are always some unintended consequences. When Gell-Mann wrote down the current algebra like that, he had this idea using PCAC or to normalize the weak currents. But somebody like Steve Adler was able to make use of this current algebra to derive this neutrino summables. And I don't think that Gell-Mann had in mind that you can do that. And that's another thing, that once you publish a paper, the paper has a life of its own. It's like, your children. Once they grow up, they do whatever they want. You have no control. So once the papers are there, then people can use them, and then have much more domain of applicability than what you had in mind when you wrote the paper. And so it's important that if you have a good paper, then people will find application for those papers. Now this is more or less near the end of this lecture, but let me say a few words. Oh, I talk about the color. And then we know that there are three colors, right? Why three colors? Because we want the barriers. I talk about omega minus. And then for three quarks to have a color singlet, then they can only have three colors. If we have four colors, this will be not a singlet. So must be three. These three colors have many applications. One is a pi 0 to theta 2 gamma. Without the color, the rate is about 10 times too small. So when you have colors, 3 squared 9 is almost 10. So that's what you need. Then the other is E plus E minus going to the hadrons. And again, without a color, the rate is too small by a factor of 3. Then the other thing is axial anomaly consideration. In the electroweak unification, you cannot have axial anomaly, otherwise the theory is not renormalizable. And the three colors, it's just right to make the constellation happens, okay? And then of course the third is the QCD is the asymptotic freedom. So one idea gives a lot of applications, important applications. Remember, sometimes people came up with the idea, solve one problem. That's no good. You have to have one idea solve many problems, at least more than one. Okay? Now, this is more or less of what happened, what we know about strong induction 1968. But let me mention one or two more things. One is in 1950, you have Yang Mills Field. This was proposed in 1954. But the problem is that nobody knew how to quantize the quantization problem. Or there are many problems, but quantization is a problem. And then masses. One problem is that nobody knows how to quantize Yang Mills field in the 50s. And also, we know that the Yang Mills gauge theory to have gauge invariance, all the vector particles must be massless. But all the vector mesons we know have masses. And so these two things together that make Yang and Mills did not make any progress besides writing down the theory. Of course, also, you remember, you know that the Yang Mills were motivated by isospin symmetry. But isospin symmetry is not exact symmetry, this is only approximate. So, in a sense, the motivation, write down the theory is very beautiful, but the motivation is not quite right, because the isospin symmetry is only approximate, and I suppose you have heard a story about Pauli. There's a strong objection because of this. When Yang was giving the seminar at the Institute, turned out that the Pauli also thought of the problem, and so he asked Yang this question. So how about the vector meson masses? And Yang did not have an answer. So Pauli kept insisting he kept an answer. So eventually Yang just sat down, did not know how to continue. And Oppenheimer was the seminar's chairman, and he felt that Pauli was a little bit too brutal to young people. So he suggested that Yang should stand up and continue to finish his story. So this problem was only solved in the late 60s. And I will come back to this later. The other thing is that renormalization group. And what's interesting is that this is also proposed in 1954, exactly the same year. And this is a law, German law. This approach did not go very far, and the reason was they discovered that in QED at least, they were driven to a coupling constant which is fixed by the theory itself, and they cannot do any calculation using perturbation. So this is can only no perturbation can be used to solve this problem. So, and again, that this is only because asymptotic freedom that the renormalization group idea was revived in the 1970s. Okay? And you see, these two things took about 20 years before people knew how to apply these ideas properly. Instead of applying to answer spin, they should apply to color. And this, because of asymptotic freedom, you can use perturbation to solve this problem. So those two are the old ideas already exist, but no progress was made. Then there are new ideas. One was Jim McKinney, Garshaw, Iliopolis, Miami. I think actually this is 1970. At the time, you only know UT and then a French code. And these guys found that you need another new code called Cham code in order to suppress new code. To forever changing neutral current. And the paper actually was very impressive because they use Fermi's 4 Fermi interactions. And then of course the degree of divergence is extremely difficult. It's very high. And they managed to classify the kind of divergences and using that 4 Fermi interaction. And to show you need this, otherwise the forever changing neutral current will be too big and there will be in violation with experiment. So that's one thing. And let me mention one thing about this paper. This paper was written in 1970s, after Weinberg's paper. That was in 1967. But they never mentioned the Weinberg's paper. Then the other thing, of course, I just mentioned the Weinberg's paper. A model of leptons. This is in 1967. And this introduced Higgs mechanism. To give intermediate vector bosons masses. Okay? And so, as I mentioned in the beginning, that Weinberg did not know whether the model is renormalizable or not. But turned out that it took 2 of them to show that it is true, can be renormalized. But this paper, as I mentioned, that did not attract any attention. And remember in 1968, very well-known physicist, Gell-Mann, flow, curl. This is not our curl, it's a different curl. And then Goldberg. And somehow they're all at the Princeton Institute. And they wrote a long paper about weak induction. Also about divergence. And they never mentioned the Weinberg's paper. So somehow Weinberg's paper never attracted any attention until 1971. The last thing I want to mention, orbital product expansion. This was Ken Wilson in 1969. And this orbital product expansion is something like this. Say A x minus 2 when x is very small. Will become some Cn x or a of 0. Something like this. And this is a generalization of equal time commutators. So, but this had to be generalized to a Lycombe expansion in order to deal with the deep inelastic electron scattering and so on and so forth. So, but when this was proposed, again, that this approach did not do very much because all these calculations require non-perturbative calculations. It's only after people discovered asymptotic freedom, then you can use the perturbation to compute these things and then get predictions, okay? Okay, that's it for today.